Today's lesson is on something called the mean value theorem. Before we talk about that theorem, we're going to talk about another one called Rolle's theorem. There are three conditions for Rolle's theorem. The first condition is if f is differentiable on the open interval ab, so these brackets are non-inclusive. That's our first condition. The second condition is if f is continuous on the closed interval ab. The third condition is that f of a is equal to f of b. The conclusion is if the three conditions are met, then there is at least one number x equals c such that f prime of c, the derivative, is equal to 0. Okay, so I want to illustrate this for you. So let's say I have some a, some b, and they have the same function value. So this would be f of a and f of b. Okay, we have to go from this point to this point. It's continuous and differentiable. Okay, Rolle's theorem guarantees that there's some point where the slope is 0. Let me draw another example. Okay, so again, they have the same function value, and it can be positive, it can be negative, it can be 0. But if they have the same value, then at least one location has a slope of 0, but there could be more. Our first example, let f of x equals sine of x on the interval 0 to 2 pi. You do have to confirm that it is both differentiable on the open interval and continuous on the closed interval, and sine of x is both of those. So we're going to evaluate the function at the endpoints. So evaluate at 0. Sine of 0 is 0. F of 2 pi is sine of 2 pi, which on the unit circle is the same location, is also 0. So that says that there is some location between 0 and 2 pi where the derivative is 0. So we're going to find the derivative, and we're going to investigate where it is 0. Cosine is 0. The x value is 0 on the unit circle between 0 and 2 pi, up at the top of the circle at pi over 2, and at the bottom of the circle at 3 pi over 2. So those are my solutions. Let's graph just to illustrate this idea. So the graph of sine, we go out to 2 pi, our graph of sine starts at 0, and goes like this. So this is a good illustration that at pi over 2, the slope is 0, and at, ignore that, at 3 pi over 2, the slope is 0. Our next equation, x to the 4/3 minus 4x to the 1/3. We're going to find n interval where the hypothesis is met, so where it's differentiable and continuous and the function values are the same. Easiest would be to find two locations where this equals 0. Okay, so I'm going to factor out the smallest common factor, which is going to be x to the 1/3. If I subtract 1/3 from 4/3, that's 3/3, so that's just x over here minus 4. Okay, so this function is going to be 0 when x is 0 and when x is 4. So between 0 and 4, the function is differentiable on the open interval, because it's actually not differentiable at 0, because if I take this, we're going to end up with a negative exponent, which means the x is in the denominator. So it's not differentiable at 0, but everything in between 0 and 4 is, and it's continuous on the whole thing. So we're going to find C where the conclusion is true. First, by finding the derivative. Subtract 1 from 4/3, we get 1/3 minus 4/3 x. If we subtract 1 from 1/3, like I said, we get a negative 2/3. We're going to pull out the biggest common factor, which is going to be 4/3 x to the negative 2/3. Here, if I have 1/3 and I subtract a negative 2/3, that is a positive 3/3, which is just 1. So the two solutions here, this is never equal to 0, because this would be the same as 4 over 3x to the negative 2/3. So it's never equal to 0, but this one is equal to 0 when x is equal to 1. To show graphically, I'm just going to graph it here on the calculator. So x to the 4/3 minus 4x to the 1/3. I'm going to just graph it. Well, yeah, we can graph it on this window. But the part we're interested in is the portion of the graph between 0 and 4. Okay, so between 0 and 4, if we look at 1, it's pretty apparent there that we do have a slope of 0 there. Next, we have the mean value theorem. So I'm going to write it all out, so you might be prepared to pause here in a second. So the mean value theorem states, if f of x is differentiable on the open interval ab and continuous on the closed interval ab, then there is at least one point C in ab, in the open interval, where f prime of C is equal to f of b minus f of a over b minus a. So what this is saying is that there's a slope of a tangent line that's going to equal to the slope of the secant line. So this is the slope between points A and B. This is some point in the middle, the slope of that point. So we're going to go through a little exploration that'll demonstrate a couple of characteristics here. One, why it's on the open interval for differentiable, but the continuous has to be the closed interval, and then just looking at this concept. All right, so number one, for the function graphed below, there is a value x equals c between 3 and 7, where the tangent line to the graph is parallel to the secant line connecting 3 and 7. We're going to draw the secant line and the tangent line. So the secant line, 3 is here, 7 is here. So we're just going to draw a line that goes right through those 2 points. Okay, so there's our secant line. Now what I'm going to do is I'm going to take my ruler, or in this case my 2015 hall pass, and just slide it up until we get a point that has that same slope. So about there. So there is a point where the slope of the secant line equals the slope of the tangent line. And looking at these values, that's about 5.5, just approximately. Number 2 here says the function has two values between 1 and 7 where the tangent line is parallel to the secant line. So here's 1, here's 7. We're going to go through and draw the secant line. So there's two locations that has the matching slope. There's the one, if I go down here, that line's going to be parallel. And then there's going to be the one if I go up. So the approximate values, this one's about 2. And this one's, I don't know, 1, 2, 3, 4, 5, still are 5.5-ish, 5.6. The next one, the function graph is not differentiable at x equals 4. That's pretty clear here. It's not differentiable here because we have a cusp. So is there a value between 1 and 5 at which the slope of the tangent line equals the slope of the corresponding secant line? So there's 1, there's 5. Okay, and if we look at this graph, there's no point here that's going to have that slope. All of these are going to be steeper, all of these are decreasing here. So that's why it has to be differentiable on the whole thing. This is continuous the whole time, but it is not differentiable at that middle point there. This is the same graph. Says that it does have a value between 1 and 4 where the tangent line parallels the secant line. So let's look at this. So if we look at 1 and 4 and draw that tangent line, okay, there is a point about right there, I know it's kind of hard to see now, that the slope is parallel. And that's because this doesn't violate the restriction, because we only have to be differentiable on the open interval. The differentiability occurs at the end point here, so it still works, and this illustrates why it works. We just can't go past that point, and that's what's going to cause it to not work. But if 4 is the end point, it still works. Number 5, this function here is differentiable on the open interval 5, 8. Okay, so this is differentiable the whole point. It's not differentiable at 5, but we illustrated that that doesn't matter. However, it is not continuous. Okay, so is there a value x equals c in 5, 8 where the slope of the tangent line is equal to the secant line? Okay, well here's 8. And 5, oh, no, there's f of 5. So the secant line is that. So is there a point here where that slope is equal? No, there is not. Okay, so it is differentiable on the open interval, so that part's fine, but it is not continuous, and it must be continuous on the closed interval for this very reason. So we're looking at the same graph, but now we're going to look, rather than 5 to 8, we're going to look from 1 to 5. It is differentiable on the open interval. It is not continuous. It's discontinuous at 5. But we're going to look to see if the conclusion is met. So yep, there's a line here where the slope of the secant line equals the slope of the tangent line. So what this illustrates is even though the conditions are not met, it is not continuous on the closed interval, you still can have a value that works even if the conditions aren't met. But there's no guarantee that there is. If the conditions are both met, then there is a guarantee there. Okay, so let's do some examples. Number 3 says let f of x equal x cubed plus 1. So first we'll graph. Okay, and f of 1 is, f of 1 is going to be 2, and f of 2 is going to be 8 plus 1, which is going to be 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll just put 1 there, 2 there. So f of 1 is 2, and f of 2 is 9. So it's just going to increase like that. So it's a little bit tough to see this, but we'll work with it. Is this continuous? Yes. Is it differentiable? Yes. Okay, so we're going to find the slope of the secant line. So that's going to be 9 minus 2 over 2 minus 1. So that gives me 7. Okay, we're going to find the equation for the secant line. So we're going to have y minus and we can use either point. I'm just going to use the point 1, 2. Okay, so there would be the secant line. Now this is going to be a little, it's going to get crowded here, but the secant line is going to be that line there. Okay, now we're going to take the derivative. So the derivative of x cubed plus 1 is 3x squared. And we're going to find where the slope of the secant line equals the slope of the tangent line. So we're going to set 3x squared equal to 7. And we're going to find the location where the derivative is 7. So x squared equals 7 over 3. So x would equal plus or minus the square root of 7/3. But we only want the 1 on our interval between 1 and 2. So for our graph, it's just going to be 7/3. Okay, we can then find the equation of the tangent line. So f of the square root of 7/3 is going to be root 7/3 cubed plus 1. And I'm just going to leave it like that. So the tangent line here would be y minus root 7 over 3 cubed plus 1 equals our slope is still 7, x minus root 7/3. The graph, going back up here to the top, the point, so root 7/3 is in here somewhere. We're talking about where the slope of this little curved piece is equal to that. Which of the following functions below satisfy the hypothesis of the main value theorem, meaning it's differentiable on the open interval and it's continuous on the closed interval? So looking at each of these equations, they all have issues with them at certain points. So we just have to figure out if the issue is on the interval. So this one is not differentiable and is discontinuous at -1, but that's the only place. So this one's fine. This one is continuous over everything, but not differentiable at 0, but that's okay because the 0 is on the end point. Had we gone from like -1 to 1, then this one would fail. But because it's differentiable on the open interval, we're good. Here, this one's continuous everywhere, but it's not differentiable at the corner, which occurs at 0, which is included here. So this one is not it's not going to work. So our solution is 1 and 2. So we're going to find a point on the interval from 3 to 10 that satisfies the mean value theorem. So we just have a parabola, so it's going to be continuous and differentiable everywhere, so we're good there. So first we're going to find the slope of the secant line. So f of 10 minus f of 3 over 10 minus 3. Now you can use a calculator to help you out with evaluating. When we evaluate, f of 10 is going to be 188. F of 3 is going to be 34. Okay, so that's going to be 154 over 7, which is going to equal 22. So that's the slope of the secant line. We're now going to find the location between 3 and 10 that has that same slope. So to do that, we need to take the derivative. And set it equal to our slope. Okay, so we'll subtract 9 and divide by 2. So there is a point between 3 and 10 at 13 halves, or 6.5. That slope matches the slope of the secant line. For number 6, we're going to find the point C where mean value is true. So we're going to do h of 9 minus h of 1 over 9 minus 1. So evaluating, 5 minus the square root of 9 is going to be 5 minus 3 is 2. 5 minus the square root of 1, so 5 minus 1 is 4. So we have negative 2 over 8, which is negative 1/4. That's the slope of the secant line. Now we're going to find where, between 1 and 9, the slope of the tangent line is also negative 1/4. So we take the derivative. That's going to be a negative 1 over 2 root x. The square derivative of square root is 1 over 2 root x. That makes it negative. So we set that equal to negative 1/4. So they're both negative, so we can remove those. They're both reciprocals. So I can just flip the whole thing over. So 4 equals 2 root x, so 2 equals the square root of x. So square it, and x is equal to 4, which is right on our interval. In the next example, we're going to show that there's no point between negative 2 and 3 where the conclusion holds. The issue here is going to be that this is undefined when x is 1. There's going to be a vertical asymptote there. But we're going to illustrate why this doesn't work. So f of 3 minus f of negative 2 over 3 minus a negative 2. So f of 3, when I plug 3 in here, we're going to have 1 over 3 minus 1, so that's going to be 1/2. Minus, when I plug in a negative 2, we're going to have a negative 1/3 over 5. So this is going to be, I need to get a common denominator here, so 3/6 plus 2/6 over 5. So we get 5/6 over 5, or times 1/5. So we get a slope of 1/6. So we're going to show that the conclusion is not true, that if I take this derivative, there is no point between negative 2 and 3 that has a slope of 1/6. So the derivative there is going to be negative 1 over x minus 1 squared. Okay, the derivative of 1 over x is this, and the chain rule, we're just multiplying by 1. So 1/6 equals 1 over negative 1 over x minus 1 squared. Well, I can rewrite this as negative 6 equals x minus 1 squared. There is no value. This is always going to be positive. So there's no value where we're going to get a negative 6. Okay, determine if the function f of x equals x cubed minus x minus 1 satisfies the hypothesis. It does. All these polynomials are going to be continuous and differentiable. If it does, we're going to find the value of c satisfying the conclusion. So f of 2 minus f of negative 1 over 2 minus negative 1. Okay, f of 2, when we plug that in, is going to be 5. F of negative 1, when we plug that in, is going to be a negative 1 over 3. So we have 6 over 3, which is 2. So we're trying to find where the derivative between negative 1 and 2 is 2. So we're going to take the derivative, set that equal to 2. So we'll add 1. Okay, so x is going to equal plus or minus 1. Now negative 1 is an endpoint. So that's not included. The conclusion is just numbers between negative 1 and 2. So the solution here, and it's going to be tricky because you're going to find those two, but the solution is just 1 because negative 1 is an endpoint. So here's a couple of AP problems. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t from 0 to 6 is given by a differentiable function c, where t is measured in minutes. Selected values of c of t are measured in ounces, are given in the table above. So first, use the data in the table to approximate c prime of 3.5. Show the computation that leads to your answer and indicate the units of measure. So the c prime, that's the slope. So we're going to look at the slope for 3.5. We're going to go from 3 to 4. So we're going to have f of 4 minus, well, c of 4 minus c of 3 over 4 minus 3. So c of 4 is 12.8 minus 11.2 over 4 minus 3 is 1. You can leave it just like this. I know it feels a little bit awkward, but on the AP test, just leave it like that. I'm going to go ahead and take it a step further for now. So this is going to be 1.6. The units. It's always going to be the units on the top over the units on the bottom. So the units on the top are ounces. The units on the bottom are minutes. For B, is there a time t between 2 and 4 for which c prime of t equals 2? This is just indicating you need to know the mean value theorem and what it tells us. So we're going to look at c of 4 minus c of 2 over 4 minus 2. C of 4 is 12.8. C of 2 is 8.8. So that's going to be 4 over 2, which, drumroll please, is 2. So since it's continuous and differentiable, the slope of the secant line, 2, has to equal the slope of the tangent line. So yes, there is some value, and we're just going to say by the mean value theorem, there is some number where c prime equals 2 because the secant line equals 2. Okay, last example. So a metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature T in degrees Celsius of a wire X from the heated end. The function T is decreasing and twice differentiable. Says, is the data in the table consistent with the assertion that the second derivative is greater than 0 for every x on the interval from 0 to 8? Explain your answer. So this is kind of a tricky question. This is actually the last part of a 4-point problem, or of a 4-part problem. So we're looking for, okay, think about what information we need. This says that the second derivative is positive, which means the slopes of the derivative are all positive. So if we can show that at some point the slope is negative for the derivative, then there has to be some value that is that the second derivative is negative. So that's what we need to show. So just looking at the numbers here, it's going down, but that doesn't necessarily mean that it's not concave up. So concave up, it says our function is decreasing. So we can decrease and be concave up. What we're trying to show is that the slopes are getting less negative. So here, this is going from 0 to 1, so it's going down 7. So the slope of that secant line would be -7. I'm going to skip here. If I go from 70 to 62 over a distance of 1, that's going to be -8. Okay, so the slope of this secant line is -7. The slope of this secant line is -8, which means at some point, let me write that down. So from 0 to 1, f of 1 minus f of 0 over 1 minus 0 is -7. From 5 to 6, and you can pick different points to verify this. Okay, we went down 8. So the slope from 7 to 8, the slopes of this graph are decreasing. So if the slopes are decreasing, that means the derivative has to be negative at some point. So I'm just going to say c prime of x decreases, and it only has to decrease at one location for this to fail. So if c prime decreases, then c prime of x has to be less than 0, because the derivative would be negative if this is decreasing. And we're guaranteed that by the mean value theorem, because the slope of the secant line would have to be negative since the slope of the secant line would be negative because this is decreasing, then the slope of the tangent line would have to be negative. So it's kind of a tricky one. This is not an obvious one, but that is how you can show that it has to be positive or negative somewhere.